Welcome to iLectureOnline. Now we're going to start looking at different portions of the galaxy in a little bit more detail, starting out with the galactic nucleus. Now here we have a beautiful picture towards the center of the Andromeda galaxy. Now of course it's not the Milky Way galaxy, but imagine at the very center of the nucleus, of the bulge of the galaxy, that's where you find the nucleus of the galaxy. And it turns out in our Milky Way galaxy, if we take a look very close at the very center of our galaxy, what we find there is a supermassive black hole, roughly a mass equivalent of about 4 million times the mass of the Sun, which would be about 10 million times the mass of an average star. So that's a very large black hole. So you can assume that that black hole has consumed roughly 10 million stars in its lifetime. And so at the very center, we have that black hole. Around the black hole, of course, we would have what we call the event horizon. And around the event horizon, we do indeed have an accretion disk. Now, the accretion disk is located somewhere at a distance from about 5 to 30 light years from the very center. So we can actually measure the location of that disk because of the X-ray radiation that we get from it. And using the Chandra X-ray Observatory, we're actually able to capture those X-rays. We're also able to capture radio radiation and infrared from that region, and with all that radiation, all that analysis, we can figure out about the size of that accretion disk. It also turns out that the influx of material seems to be coming from the north, so to speak. If you think it is as the north or the z-axis, the influx of material comes from the north and forms an accretion disk around the black hole. Now, the region is known as Sagittarius A because we're looking in the constellation Sagittarius, and so that's why it's called Sagittarius A. It's at the very, very center of our galaxy. Now, we've been able to capture the shift, the red shift and the blue shift of the material swirling around, and based upon that red shift and blue shift, we've been able to calculate the speed at which the material goes around, then knowing the distance that the material is away from the central black hole, and from that we can calculate the size of the black hole by using the orbital equation, the orbital velocity equation. So V orbital is equal to the square root of g times m divided by r. So if we can capture the velocity by the redshift and blue shift of the radiation coming from the accretion disk and from the stars nearby, because we can also capture some of the star light in the infrared that makes it through the gas clouds. And so by measuring the speed of the stars, by measuring the speed of the material in the accretion disk, and then knowing the distance from those stars and the distance from the accretion disk and the in-swirling gas to the black hole, we're able to get this, and g of course is a constant. From that we can calculate the mass inside that black hole, and that's how the estimate has come about to be about 4 million. Now that number of course is not an exact amount. I remember just a few years back that it was estimated about 1.5 million times the mass of the Sun, but with better measurements and better capability, we've been able to figure out exactly, not exactly, but closer and closer to probably the true value of the mass of that black hole. So that's the nucleus of our galaxy. We do have that black hole. It is somewhat active. It's not as bright as you would think a quasar would be. Of course, a quasar would be much more active than this, because quasars are, of course, where galaxies are actually colliding, and the amount of material falling into the black hole is way greater in those circumstances than we have going on inside our own galaxy. There's just probably some gaseous material that gets too close, gravitationally gets pulled in, that sets up the accretion disk, that sets up the activity of the black hole. So there's enough activity taking place that we see the X-rays, we see the radio emissions of the events happening at the very core of our galaxy, and that is how we know.
What's between the event horizon and the accretion disk?
Well, what's between the event horizon and the accretion disk? It's basically material that slowly, like a whirlpool, falls into that region. So it's not like the disk is just swirling and not falling in. There's this continual material that slowly gets pulled like a whirlpool into that center region.
Or is it lightish?
It's going to be bright. It's going to be bright because it has X-ray emissions, probably some ultraviolet. There's probably some visible light that, of course, we can't see the visible light. But yeah, it's not black there. It's just swirling material that falls in.
But not as bright as the accretion disk?
The accretion disk is where the bulk of the material is that's swirling away, so that might be where more of the emissions are coming from than from the infalling material. Yeah.
But everything from the event horizon in is black?
Yes, anything beyond that, you can not see a thing. But then, of course, that region is so small, you wouldn't be able to see it anyway. It's too tiny to be seen.
So the event horizon is really tiny?
Yeah, if you want to calculate the size of the event horizon, it's the number of solar masses times 2 miles, or 3 kilometers. So it would be 12 million kilometers. At a distance of 28,000 light years, that's so tiny you wouldn't be able to discern it.
But inside the black hole is infinitely small?
And you would assume that the size of the black hole itself, where all the mass is at, is very, very tiny, presumably infinitesimally small, yeah.
And we have that inside the Milky Way?
So this here is at the very center of our Milky Way galaxy, right?
Is that to scale or is it much smaller?
No, not to scale. This would be like a pinprick. You couldn't even see it. It'd be that tiny. Yeah, so if you make a little pinprick, right in this picture right here, if you assume this is the Milky Way galaxy, make a little pinprick, that would be about the size of this region. Yeah, very, very tiny. That's what we mean. It's the galactic nucleus. It's the very, very center of our galaxy. It's a big galaxy.